Hi, everyone. Welcome to the last session of the day. We're going to hear about batch threshold encryption and its applications in mempools. And we will start with a talk about partial fraction techniques. And Nusret will be giving the talk. The floor is yours.
Yeah, thanks for the introduction. Hi, everyone. I'm Nusret, and I will be talking about partial fraction techniques, foundations, and efficient batch threshold encryption. So this talk is based on two papers that are joint works by and with Boneh, Charanjit, Jutla, Rohit, Nema, and Arnab. So here are a few important disclaimers. None of the views here should be taken as financial or any other advice. Okay, let's jump in. So the motivating problem at the heart of this talk is maximum extractable value, or MEV. So to understand this issue, we need to look under the hood of what happens when a client sends a transaction to the blockchain. So these transactions, they first go into a public pool of transactions called the mempool. Then, in the ideal scenario, a validator basically picks up a subset of these transactions and proposes them as a block. However, it could as well be that this validator or the block proposer is adversary, and it can insert its own transaction before a victim transaction, and in the process, extract value from it. So thus the name maximum extractable value. So this could also happen in the form of backrunning or sandwich attacks. So encrypted mempools have been proposed as a solution to this problem. So what happens in encrypted mempools? The clients encrypt their transactions, and they send them to the mempool. Now our adversary proposer does not know anything about the transaction contents, so it will be harder for it to extract value. However, there is a problem here. How do we eventually decrypt these transactions, right? Now, ideally, we do not want to rely on the client themselves to come back to the system and decrypt their own transaction, because these clients could be offline or malicious. Okay, so the first idea to this decryption problem is just to rely on these N validators to publish shares of a secret key. Okay, so how does this solution work? So in this idea, each client encrypts its transaction with respect to a public key associated with a target block. So here the public key 1 is the public key associated with the first block. Now the first block is proposed, like containing a subset of the transactions encrypted under public key 1. Again, our adversary proposer doesn't know anything about the contents. Now this block gets confirmed, and now these transactions need to be decrypted. So how does this happen? Each of these N validators, they're going to publish a share of the secret key SK1 corresponding to this public key PK1. And upon collecting these, a large fraction of these secret key shares, we can derive the secret key and then decrypt the block. However, there's an issue here. It might as well be that not all of the transactions encrypted under public key 1 are included in this block. So some of them are still in the mempool, but we can use the secret key SK1 to also decrypt these transactions, right? So this idea has the problem that there is no privacy for the pending transactions in the mempool. Okay, so now let's solve this problem. So here's our second idea. We can publish, or the N validators can as well publish these decryption shares. So how does this idea work? The clients now encrypt their transactions under some global public key PK, and let's suppose there are like L transactions per block. Again, a block is proposed and confirmed, and now we need to decrypt these transactions. And now what happens is that each of these N validators, they publish a decryption share for each transaction that was included in the block. Okay, so now you already see the problem here. There are like L transactions in the block, and there are N validators, and each validator has to publish a decryption share for each transaction. So that basically makes the communication complexity N times L. So this is quite large, but if you brush this issue aside, this solution, this idea actually works. So you can combine these decryption shares for each transaction and obtain a decryption key for each transaction and decrypt each transaction. So these decryption keys, they don't work on any other transaction outside the block, so we don't have any privacy issue for the pending transactions. But we have the communication problem. Okay, so far we have seen two ideas: publishing secret key shares, no privacy for pending transactions; publishing decryption shares, or also more formally known as threshold decryption, high communication complexity. So now this these observations, it begets the question, can the L transactions in the block be decrypted by a single succinct decryption key in the number of transactions, right? If we had such a system, then we could basically have each validator publish a share of this, a single share of this single succinct decryption key. So in our paper, we answered this question in the affirmative, and then this construction is called a batch threshold encryption construction. So now we had the threshold decryption, and we added the word batch here. So batch means that each validator now publishes a single decryption share for all of the L transactions in the block, and combining these decryption shares, we obtain a single decryption key for all of the L ciphertexts. Okay, so in a nutshell, how does this work? Clients again encrypt their transactions under this global public key, and then there are again L transactions per block. A block is proposed, it gets confirmed. Now, each of these N validators, they publish a share of the single decryption key. So in total, there will be order N decryption shares. So if you combine these, you obtain a single decryption key that helps decrypt all of the ciphertext in this block and nothing else. Okay? So this is our answer to this decryption problem in encrypted mempools. Okay, now I'll switch gears a little bit and talk about the techniques of how we actually achieve this. So the main technique we are going to rely on is partial fractions that were introduced by this paper by Charanjit, Rohit, and Arnab. So the key idea in the partial fraction technique is actually a seemingly simple but very powerful idea, which is that partial fraction decomposition allows linearizing cross-term products with different indices. Okay, so that's a lot of words. What does this mean? I think this is best expressed with this visual matrix. So in this matrix, at each entry of the matrix, at row I and column J, you have the product of two fractions, 1 over x plus I times 1 over x plus j, okay? So now, in the off diagonals, these I and j terms are different, right? And now from basically basic but powerful math, we know that 1 over x plus I times 1 over x plus j can be decomposed or like linearized as 1 over x plus I minus 1 over x plus j times some constant terms, right? So if you apply this idea to this matrix, what happens is that all of these off-diagonal terms actually become linear in these partial fractions. But the diagonal terms, they do stay quadratic. Okay, so we need to remember this because we will use this to construct the batch threshold encryption. So let's go on. So how we use this idea? Well, before I dive into the details, let me give an overview of like how batch threshold encryption is constructed from smaller pieces. Then we will attack the problem piece by piece. So we first construct a simpler object that I would like to call index-dependent batch encryption. So it's simpler for two reasons. There is no threshold here. It's just batch encryption, right? There is a single party who has a secret key, and then it uses the secret key and a bunch of ciphertext to generate the decryption key for this batch of ciphertext, okay? The second simplification is that it's index-dependent, meaning when you're encrypting your transaction, you specify an index from 1 to L and encrypt your transaction to that specific index. And when a decryption key has to be published, it needs to be published for a batch of transactions where each transaction was encrypted to a different index. So we do not allow index collisions in this batch. So that's a weaker object than batch threshold encryption. Now we resolve this index limitation by combining this with broadcast encryption from the paper, partial fraction techniques for cryptography. And in the process, we obtain a full batch encryption. However, this is still not threshold, right? This is just batch encryption so far. Well, the last step in the construction is to thresholdize it to get the batch threshold encryption. So this is how we obtain our end object. But now in the rest of the talk, I will focus on the first piece, which is index-dependent batch encryption, and it will illustrate how we use the partial fraction ideas. Okay, so let me start with a brief intuition. So let's remember the matrix and partial fraction decomposition that helped us linearize the off-diagonal terms. So the first idea in the batch index-dependent batch encryption is to use the quadratic poles, these quadratic terms 1 over x plus I squared, etc., at the diagonals as a one-time pad to hide the transaction, okay? Because now we need to do encryption, like index-dependent batch encryption. We're going to use these quadratic terms as our one-time pad. Okay, so the second step is, as the decryption key, we will publish a sum of partial fractions. So basically, the sum of 1 over x plus j's. Okay, so this is how the decryption key intuitively looks like. Now, the crux of the matter happens at the time of decryption. So in decryption, what you do is the following. Suppose you want to obtain the transaction that was encrypted to some index I. So that's why I was talking about index dependency. So you have this transaction I that was encrypted to index I, and you want to obtain that. The way to do that is you take the decryption key, which is the sum of the fractions, and you multiply it with 1 over x plus I, where this I term is the index of the ciphertext, right? Now, but our decryption key is basically a sum of fractions. And what happens when you multiply a sum of fractions with 1 over x plus I? We basically get a sum of all the terms in this matrix at the ith row. Okay? So let me repeat that. So we have the decryption key that's a sum of partial fractions, 1 over x plus 1 plus 1 over x plus 2 plus 1 over x plus 3. You multiply with 1 over x plus 1. You basically get the sum of the terms at the ith row of this matrix, okay? But in any row of the matrix, there is only one diagonal term, and all of the other terms are off-diagonal, and we have seen that you can linearize the off-diagonal terms. So once you linearize the off-diagonal terms, you obtain this quadratic pole, 1 over x plus I squared here, and then you obtain a sum that is linear in the partial fractions. But now, because that remaining sum is linear in the partial fractions, now the decryptor can peel off this term and obtain this quadratic pole. And remember, the quadratic pole was our one-time pad, so it can obtain the transaction. So let's make this more concrete as the last step of the talk. So recall that we have a batch size of L, and let's compile this intuition in the previous slide using groups equipped with a pairing operation. So at the setup phase, the setup algorithm samples a field element, and it outputs partial fractions from like 1 over x plus 1 to 1 over x plus L. Remember, we have L slots in a block in the first and the second groups, respectively. So these are our public key, and our secret key is simply this field element x. Now, encryption looks very much like Al-Gamal encryption, except that our one-time pad is now, as I mentioned, our quadratic pole, okay? So ciphertext has a first part, which is this randomly sampled element R in the first group, and a quadratic pole scaled by this R as the one-time pad. Okay, so now how do we publish the decryption key to decrypt the block? Well, again, it's basically a sum of partial fractions scaled by the first parts of each ciphertext. And by definition, this is basically equal to sum of partial fractions in the first group scaled by these random field elements that went to each ciphertext. And to decrypt, we take this decryption key in the first group, and we apply the pairing operation. You can think of this pairing operation as the product with the partial fraction term, 1 over x plus I in the second group, okay? Now, again, we obtain a sum paired with 1 over x plus k in the second group. And then this can be written as the sum of the quadratic pole term plus a bunch of cross-term products, but with different indices. And these cross-term products with different indices, they can linearize, and they can basically be expressed as the first parts of each ciphertext paired with these public elements, which are the partial fractions in the second group. And because these blue parts that are in the second group are public, now the decryptor can basically obtain the sum by pairing the first parts of each ciphertext with them, peel it off, and then leave the quadratic pole term alone. And this way, it can decrypt the transaction. Okay, so we are not the first people to introduce the term batch threshold encryption or to give a construction for it. So there has been a lot of earlier works. So this is a table from our paper. However, these earlier works, they had some limitations, such as index dependency, which we have just talked about, some epoch issues, or like a large CRS or large public keys in theory. So we basically resolve these limitations, and we obtain an index-independent epoch-less construction with like public keys that are only like linear in the size of the batch. And there has also been some subsequent works after our paper that would constitute the state of the art. So these are also batch threshold encryption schemes without these limitations. And yeah, so this is my last slide. If you don't remember anything at all from this presentation, I would like you to take away the idea that partial fraction decomposition, seemingly a simple idea, is very, very powerful. Like we use this to solve a hitherto open problem, batch threshold encryption, without any of these limitations. And it has been also used to solve broadcast encryption or threshold encryption with useful features in the earlier paper. So please learn these techniques and try to attack problems you're interested in using them. So you can also check out our papers at these QR codes. And thank you.
Thank you very much, Nusret, for the nice talk. If you would like to gather for questions. Meanwhile, I would like to ask, could you elaborate what does it mean for your scheme to be epoch-less, and what in particular of the partial fraction techniques allows a scheme to be epoch-less?
Yeah, that's a nice question. So first, what does epoch-less mean? So the first paper to introduce batch threshold encryption solved this problem by designing actually a stronger object called a batch identity-based encryption. So in that case, what happened was everyone encrypted their transaction to an identity. And then in the ideal case, what would happen is that we will publish a secret key for a batch of identities, and that secret key will help decrypt any transaction encrypted under this batch of identities. But now it had this epoch limitation where the transactions were encrypted not only to an identity, but also an epoch number, and a secret key can be published only once per epoch. So what this implied for encrypted mempools is that you were gonna select a block for your transaction to be included, and then encrypt it to the epoch ID of this block. And if your transaction was not included by this block, then it cannot be included in future blocks. So that was the issue. But of course, in practice, there has been solutions that get around this. So there will be a paper, I think, presented right after mine that resolves this theoretical limitation by using a DKG method on blockchains. So I will leave it to the next presentation. Okay, so second question very briefly, sorry. What in partial fractions helped us? It's basically this decomposition idea of the non-diagonal terms that helped us basically avoid the epoch limitation.
I see, thank you. Next question, please.
So I guess earlier today we heard that quantum computers are coming in 2030, and these methods are all pairing-based. So what do we do in a quantum world? Okay,
so well, not all is hopeless there. So I actually have a different paper that has a plausibly post-quantum secure lattice-based constructions for batch threshold encryption. So it in fact includes two constructions. One of them is a batch identity-based encryption. One of them is, I would say, like a post-quantum, plausibly post-quantum secure version of BeatMem. So I would encourage you to, check out that paper as well. So we do know post-quantum alternatives. They are, of course, not as efficient as right now, but I'm pretty sure there will be a lot more improvement in their efficiency in the future.